This is Chapter 10, the last chapter of the course on what's called hypothesis testing. This is kind of familiar to running a science experiment, and it's also familiar or similar to the court system. In the court system, you're innocent until proven guilty. So if you're familiar with the American court system, we assume the person is innocent until there is enough evidence to prove that they are guilty. If we cannot prove they are guilty, they get a not guilty verdict. So we're going to kind of talk about hypothesis testing in those same terms. The whole idea of hypothesis testing is that we have to come up with evidence to prove what we're trying to prove the guilty verdict. So the first part of Chapter 10, Section 10.1, is all about the language of hypothesis testing. The wording in Chapter 10 can get a little confusing. So it's really important that everything logically makes sense to you. You can draw pictures if you need to kind of help you visualize what it is we're trying to test. And then the last two sections of Chapter 10 are pretty quick on actually running a hypothesis test. But we're going to spend a good amount of time in Section 10.1 just setting up the language and thinking for hypothesis testing. So the example your textbook opens up with is a question about, is your friend cheating the game? So a friend of yours wants to play a simple coin flipping game. If the coin comes up heads, you win. If it comes up tails, your friend wins. Suppose the outcome of 5 plays in the game is tails, 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 tails. Is your friend cheating? So think about what your gut reaction is to this. If you're playing a game with someone and you lose 5 times in a row and they win, tails, 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 does your gut say, I think you might be cheating. I think something's going on that's not fair. So let's think about how we can mathematically determine if this outcome, tails, 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 is unusual. So we've talked about unusual before, less than 5% chance of happening. Each time you flip a coin, you have a 1 out of 2 chance of getting tails. We flip the coin 5 times. Each flip is independent, so we can multiply these together. You can also use 0.5 if that works for you as well. So we can write that as 1/2 to the 5th power. And if you compute that percentage, it's 0.03125. So there's only a 3% chance of getting 5 tails in a row, which is less than 5%. So yes, this outcome is unusual. And so I've kind of talked about in the previous chapters, we're curious about these unusual outcomes. They pique our interest. If an outcome is unusual, 2 different things can be happening. It could be that your friend is not cheating and just happens to be lucky. So they look guilty, but really they're innocent. Nothing's going on. The other option is that your friend is cheating and using an unfair coin. So maybe the coin's weighted. Maybe he's flipping it a certain way that's making it not land on heads. That would be guilty. That would be, this is so unlikely that you might be guilty. So anytime we get unusual results, it could just be by chance, or there could be something going on that's unfair. And that's what hypothesis testing is all about. So we're going to kind of go through the pieces of setting up a hypothesis test, and then we'll actually run them in sections 10.2 and 10.3. All right, so a hypothesis, you might have heard that word before. A hypothesis is a proposition or statement assumed as a premise in an argument. So if you've run a chemistry lab experiment before, you come up with these predictions of what you think is going to happen or what you think is going on. So that's what a hypothesis statement is. It is a statement regarding a characteristic, whatever it is you're measuring, of one or more populations. So whatever we're trying to test, this statement makes some sort of conclusion about that characteristic. I think the test average is this number. I think the average height is this value. So whatever we're trying to test, it comes up with some sort of statement about that characteristic. So hypothesis testing is a procedure based on sample evidence, which is data, and some probability, and together it's used to test these hypothesis statements. Are they true? Are they not true? So I'm going to try to keep this as simple as possible. If you are going into the legal field, you might have to learn a little bit more about this. This is all how a court system works. Again, if you're going into research, you'll learn more about running a proper hypothesis test. We're just going to study the basics and try to keep it as simple as possible. So the steps in hypothesis testing is to make a statement regarding the nature of the population. There's actually two statements that we're going to study. Then you collect your evidence or your sample data to test your hypothesis. This part's going to be done for us. We're going to kind of skip that step for our class. That's the fun part, but we're going to skip that step. Once you have your evidence, you analyze the data to assess the plausibility or likelihood of the statement. And once we've analyzed the results, we make a conclusion based on the probability of our analysis. So we're going to learn how to make the statements, then we're going to learn how to make the conclusions, and then we'll go back and learn how to run the tests in the calculator. But right now we're going to focus on statements and conclusions. So there's two types of hypothesis statements. The first one is called the null hypothesis. It is a statement to be tested. It is a statement of no effect, no change, or no difference. It means nothing's going on that's any different than what's been going on. It is assumed to be true until evidence indicates otherwise. So we write this as HO for null hypothesis, H with a little 0 or O. That's your null hypothesis. And then there's the alternative hypothesis. That's abbreviated H with a little a, or I think this textbook uses H with a little 1. So H null is always with the little naught or 0. And then HA or H1 for alternative. Again, I think this textbook uses H1. That is the statement we're trying to find evidence to support. So we're trying to support the alternative. We're trying to reject the null. We're trying to say that the null is no longer true. So we have the null and the alternative. So there's three possible setups for the null and the alternative hypothesis. The null hypothesis is always equal. So it's the parameter, whatever we're trying to measure, equals some value, whatever that value is. And then the alternative, one way to write the alternative is that it's not equal to the value. This is what we call a two-tailed test. So I might claim that my test average is 70 for my classes, and someone might come and say, you know what, I don't think it's 70. Might be less than 70, might be more than 70, but I don't think it's 70. So it's called a two-tailed test because if you think about your bell curve, we're going to be testing the upper tail to see if the average is much greater than 70, and we're going to be testing the lower tail to see if it's much lower than 70. Your null is always in the middle. That's where your null goes. The alternative's trying to prove that the data is down here in this tail or up here in this tail. Then we have equal to versus less than. Again, the null is always equal to. whatever value you're trying to test. And you could test and try to prove that the parameter is less than some value. So I might say that my test average is 70, and someone might try to prove that my test average is less than 70. We call that a left tail test, because I'm trying to prove that the null is in the middle and my data falls in the left tail. So left tail test. And then we also have a right tail test. And again, the null is always equal, that the parameter is equal to some value. And we might be trying to prove that it's greater than some value. So the three setups are not equal to, less than, or greater than for the alternative. The null is always the same, always equal to. So again, I might say that my test average is 70, and someone might be trying to prove that it's greater than 70. Just quick examples there. So again, the null's in the middle, and maybe I'm trying to prove that my data is way up here in the top of the curve. So two tail, left tail, right tail. The left tail and the right tail are also called one tail test, because we're just testing one side of the curve. So let's practice writing these null and alternative hypotheses. So the first one says the Medco Pharmaceutical Company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. So 2% is kind of the baseline. A researcher at the FDA wishes to know if the percentage of children taking the new antibiotic who experience headaches is more than 2%. So our baseline is 2%, and we're trying to prove that the new medicine is more than 2%. So we're talking about a proportion here, so we're going to use P for proportion. We're assuming the baseline of 0.02, and we are trying to prove that it's greater than 0.02. So you have to think about what kind of parameter are you measuring. Are you measuring a mean, a percentage, or a standard deviation? Use the proper letter for the parameter. Remember, the null is always equal, and then it's the alternative that's either greater, less than, or not equal to. On the next one, it says the Blue Book price of a used 3-year-old Chevy Corvette ZR1 is $86,012. Grant, some guy, wonders if the mean price of a used 3-year-old Chevy Corvette ZR1 in Miami is different from the $86,012. So we're talking about averages here, so the mean, we assume it to be the baseline price of $86,012, and we're just trying to see if it's not equal to $86,012. Maybe it's more, maybe it's less, but we're just trying to see if it's significantly different from that $86,012. And the last example, the standard deviation of the contents of a 64-ounce bottle of detergent using an old filling machine is 0.23 ounces. The manufacturer wants to know if the new filling machine has less variability. So this time we're measuring standard deviation. So we're going to use sigma. We're going to assume it to be the same as the old machine, and we're trying to prove that it has less spread than the old machine. So again, the null is always your equal to, and the alternative is always your inequality, either not equal to, greater than, or less than. So that's writing a proper hypothesis statement. You'll have to read the problem to know how to set up your statements. Later on, we're going to learn how to run the calculations. And once you run your calculations, you're going to have to state a conclusion. Now, this is where students get a little confused about how to state the conclusion. I'm going to explain it a few different ways as we go along. So, first thing to remember is that you always state your conclusion in terms of the null hypothesis. You either reject the null hypothesis or you fail to reject the null hypothesis. So those are your two options. You either reject or you fail to reject. So if you reject the null hypothesis, then there is sufficient evidence. Instead of sufficient, sometimes you'll see the word significant or enough. Just other words that mean the same thing, significant or enough. Evidence to support the alternative. So you reject the statement that says equal to, and you support the statement that's either less than, greater than, or not equal to. So you always reject the null or fail to reject the null, and then you have evidence to support the alternative or not enough evidence to support the alternative. So if you fail to reject the null, then the second statement is true. So if you fail to reject, and we'll talk about when we do which one in a little bit. If you fail to reject the null, which is the second option, there is not enough or sufficient significant evidence to support the alternative. And again, the alternative is the one with the inequality. So you either reject or you fail to reject the null, and that decision determines the rest of the conclusion. So you have to really watch your wording. You either reject or fail to reject the null, which is the equal to statement, and you either support or do not support the alternative statement. And your textbook kind of talks about why we use that wording. Again, if you think back to court, we never declare defendant innocent, but rather we say the defendant is not guilty. So just because you get a not guilty verdict does not mean that you're innocent. I don't want you to overthink that. I just want you to practice this wording. This is where students get confused the most on how this wording works. And I'm going to try to explain it as we go along, and hopefully it'll start to kind of sink in. But it is very particular on how the wording works. All right. So let's practice writing conclusions real quick. And then we'll get into what happens when an error occurs. So it says the medical pharmaceutical company is trying to test those children with the headaches. We have a null of 0.02, and the H1 is the greater than 0.02, same as before when we were practicing our statements. Part A says the null hypothesis is rejected. State the conclusion. So if you reject the null, you have enough evidence to support the alternative. Now, in this specific example, the alternative is more than 2% of children get the headaches. So remember, the alternative is the greater than one. If you fail to reject, if it's not rejected and you fail to reject, there is not enough evidence to support the alternative. That doesn't necessarily mean that the alternative is not true. It just means you've not found enough evidence to support it yet. So again, if you reject the null, you support the alternative with enough evidence. If you fail to reject the null, you do not have enough evidence to support the alternative, and that is how we state our conclusions every time. I'm going to go ahead and stop there, and I'll record a separate video to talk about errors.